Now let us take one example. Let us take one example where rearrangement makes a difference here. So I have a tertiary butyl attached to the alkene. When I am adding the water to this one in presence of sulfuric acid H2SO4, I said the proton of the sulfuric acid first adds on the carbon so that the more stable intermediate, this is the step 1, right? So you get a carbocation on the second carbon, and where one hydrogen is added. Step 1 is over actually. Now the without rearrangement means the water should attack here, leave the OH. So without rearrangement means this is the product you expect. The O will become OH and this one. But you also get this carbocation undergoes a rearrangement. This is, I am showing a symbol for the rearrangement. In the rearrangement, what happens? This is already 2 degree. So if this H comes, it will become 1 degree. But this side we have a CH3 taking the 2 electrons will jump onto this carbocation, so that the carbocation will become now into a 3 degree one. See, this side you get a methyl. So this will become a 3 degree carbocation, right? Now this 3 degree carbocation naturally will more stable, so therefore this will become into 3 degree and then undergoes the addition of the water. That means water will attack here and leaves the OH and H will come. So what is the unexpected product is this is your unexpected product. This is a without a rearrangement, first one, with rearrangement this one. With rearrangement this answer many times when there is a chance is there, the rearrangement is inevitable, because 2 degree to 3 degree is a upgradation. So carbocation will have a right for this upgradation. So whenever 1 degree comes, it will become into 2 degree, 2 degree become into 3 degree and so on. Even the rings expansions also, Demjanov ring expansion one side, we have seen that. All such things are inevitable, you can't stop. So therefore rearrangement it will take, and then the product also will become like. Now I don't want this rearrangement answer, I don't want. In such a case what you do is, you add this, first you add the B to H6, right? So you will get a boron added to the last carbon, right? That is Hg OAC taken twice. So you will have a mercury attached system here, Hg and OAC, that is acetyl group is shown as a AC. Now this Hg will have a tie-up with this carbocation. That's why there is no rearrangement, I said. So now when aqueous water is there, this will become into OH, then on reduction this one. So first water, aqueous solution will there, so therefore water will attack here and replace this one, followed by the B, that is sodium borohydride. Sodium borohydride reduction takes place and you will get the, so without any rearrangement, the tertiary butyl will be like that only, the OH will come. This is without rearrangement as such will come, because of this mercuric acetate making a tie-up with this carbocation. No rearrangement takes place, water will come and then reduction, that mercury will come. So without rearrangement, no rearrangement, we get this reaction. So without rearrangement you will get this, okay. This is the addition of water followed by the sodium borohydride reduction, both taking place one after the one, then you will get this no rearrangement containing the alcohol comes. If ordinarily if you do, always it goes to the with rearrangement will become the major product, and a small quantity may go to this one, but it is left to the chance of that molecule. So here if I do this mercuric acetate addition followed by the reduction by the sodium borohydride, I am curtailing that rearrangement chance, and you are getting without any rearrangement product getting, is the significance of this oxymercuration and the demercuration. Okay, let's take the second reaction, that is oxidation reaction. In the alkenes, oxidation is also one of the important reaction because we have a big number of oxidizing reactions, pattern of the oxidation will be different and so on. So simply one oxidation is there with the alkaline KMnO4. Alkaline KMnO4. It is introduced by a scientist called Bayer. So therefore it is also called Bayer's reagent. Bayer's reagent. But actually the Bayer not introduced alkaline KMnO4. He introduced a dilute, cold, aqueous, neutral KMnO4 as a reagent, and under all these four sensitive conditions the oxidation will be very mild and the products he established as a glycols formation and so on. Later identified the permanganate anyhow in the reaction with water, finally becomes a KOH solution is formed, that will become alkaline. So therefore initially only alkaline, if it is maintained, same reaction is obtained. So therefore it is said that the permanganate alkaline medium means either you take K2CO3 or KOH, either one you make alkaline solution and then add it, say mild oxidation takes place. Sulfuric acid, when you add, it will become stronger oxidation. So I am now specifically we are doing here mild oxidation. In this mild oxidation, all alkenes like ethylene for example, when it is treated with the permanganate, MnO4 minus is actually the oxidizing agent here. This attacks on the alkene and gives a compound like this in fact. So a O and Mn through O and then a double bond and a O minus, and the groups will be as it is. This is what formed, outside K plus will be there. A salt formation is taking place. The whole MnO4 will have a pink color. So the K is not colored, it whether it is sodium or potassium makes no difference. So this is what actually pink colored. So the permanganate will have a dark violetish pink color will be there. That solution when you add, so the MnO4 attacks from one-sidedly. See carefully, MnO4 comes from one-sidedly, whereas in the bromination one comes from that side, one comes from this side, that's different. In this case it is from one side it is coming, it undergoes hydrolysis with water and then becomes into a, this part will become MnO2, so that side you will get the two OHs. This 2OH containing compound is called glycol. So from ethylene I got, so therefore it is commonly known as ethylene glycol. Ethylene glycol. So the complex decomposes into ethylene glycol, wherein two OHs are formed. Specifically we want to say that the two OHs, because they are attached to one-sidedly, the OH come from the same side, so this is called cis type of glycol is formed. However, in the case of ethylene, it's a single bond, it is there, so it rotates, whether the OH is formed from the opposite or same side, same ethylene glycol comes. But there are some cases where we differ. So in the ethylene case, we are getting a ethylene glycol, and by nature the OHs are same side. You can observe that they are coming from the one-sidedly cis. Is it cis glycol means ethylene glycol rotates and becomes cis into trans into cis, there is no point. So conformational isomers will be formed, but that's all. So in ethylene case it is glycol. So wherever the double bond is there, you open pi bond and create two OHs side by side, that is 1,2 diols are formed. If a propene is taken, propylene glycol, butene, butylene glycol, and so on. It's a very simple reaction, but it has one significance because of the color. Just like in the bromine also, bromine is a red colored one, so you add one drop to the alkene, consumes that red color, becomes colorless. Here also the pink color, after the reaction this Mn will become into MnO2. This MnO2 is a precipitate actually, and it is having a very light brown color will be there, and moreover in the test tube and the small quantity of MnO2 will be formed at the bottom of the test tube. So, therefore, entire test tube will be colorless and the small light brown color precipitate will be observed at the end. So, therefore, really speaking the pink to colorless you are getting therefore. So, this is what the test in fact. You can use it as a test. You take alkene, add 1 drop of pink colored solution, that is Bayer's reagent. After some time the pink color will become colorless because of the consumption of KMnO4, MnO4 minus becomes into MnO2. So, the color is discharged. So, therefore, and E9 ine, if it is E9 ane is there, how do you differentiate? If the question comes for both you add the same reagent. In the case of ene positive reaction, in the case of ane negative reaction. Negative means no reaction. The pink color remains as such, that is called negative reaction. Pink color changes, that is positive reaction. So, E9 ane, how do you differentiate? Add Bayer's reagent. This works with bromine CCl4 also. Bromine also decolorizes and no reaction. Now, similarly, if ine ane is also reaction successful, but ene and ine is there, both react, therefore, you can't differentiate. So, specifically in the chapter alkenes we can discuss. Alkenes can be differentiated from the alkanes using with the Bayer's reagent, as well as previously we have seen bromine and CCl4, both reagents can be used. This is the alkaline KMnO4 reaction. Second type of the oxidation, this is epoxidation followed by hydrolysis. So, an ethylene if you take, you add a reagent like a carboxylic acid holding 1 oxygen extra is called peracid, or a hydrogen peroxide and water, or silver and oxygen, okay, Ag2O. Some reagents which can supply the nascent oxygen may be added. That nascent oxygen will added over the double bond to become into a small ring type of the compound is called. They are called cyclic. COC bond is ether bond. So, it is a cyclic ether. It is an example for cyclic ether. In this ether, a 3-membered ring with oxygen is called epoxide. It is. So, you can say systematically epoxyethane. Epoxyethane is formed. All ethylene gives a epoxide, therefore, it is called ethylene oxide or ethylene epoxide. They are called epoxides. These epoxides, when you hydrolyze with water in presence of either with the H plus, or you can have water in presence of base medium also. Either way you can hydrolyze, so that this O, the bond breaks and this will become OH. One more OH will come and 2 OHs are coming, but these 2 OHs carefully if you observe, 1 OH will be from the upper side, water comes from this side. So, therefore, trans type of products are formed. However, once again I will explain, this is a single bond, so therefore, it rotates. So, trans type, that means anti type will become into syn, syn will become anti, but the addition is a trans pattern. You have to remember this. We do some exercises on the other compounds, but right now the previous case first time, that is permanganate alkaline medium, if you use, OHs come from the same side. In this case it comes from the opposite side. So, in the example of ethylene glycol, for example, ethylene you take, do some exercises here. In the case of ethylene, you get this the first reaction or second reaction. So, in the first reaction OHs are same side, in the second reaction OHs are opposite side, isn't it? So, what is the relation between, means these two are conformational isomers. Conformational, it rotates, single bond rotates, therefore, that becomes into, that means even if you prepare this one, it changes into that, that changes into this. But if I take a compound like this, a cyclohexene if I take, then these two reactions differs and gives a different answers. Alkaline KMnO4 will give the a cis glycol. Two OHs either will be down or will be up. But in the other case, two OHs will be in the, one will be up, one will be down. So these two are now, what is the relation means they are geometric isomers, that is cis trans isomers. One is a cis compound, one is a trans compound. So geometric isomers, or you can say cis trans isomers, are formed on the alkene, that is a cycloalkene will not rotate this single bond. So therefore they are fixed. One will become cis compound, another will become trans. Much more interesting is if you have a tubutene which is having a geometric isomerism, the compound itself tubutene and trans tubutene. Cis tubutene if you add, you will get a meso compound. Trans tubutene will become the D and L mixture, that we will see later as a stereospecific addition. Right now it's enough that first type of oxidation, that is alkaline KMnO4, gives a cis type, and epoxidation followed by hydrolysis will give the trans type. In the hydrolysis also we have a one small point is there, we will see that. So specifically in the hydrolysis part, we take a alkene containing some alkyl groups, let us take like this. One side alkyls are there, one side, other side alkyls are not there. Then we add the epoxidation, that is first epoxide is formed, right? But alkyl groups are there, okay? Now the hydrolysis you are doing in a different way. Hydrolysis using the acidic medium. Hydrolysis using the acidic medium. What is the mechanism means here? The H plus attacks on the O, you will get in a epoxide get like this. This is called what? Oxonium ion salt formation. Then undergoes a breakage. Okay. While breakage, either this side can be opened, that side can be open. So therefore you have a two chances of getting the open up. So you may get that side a OH and carbocation may be formed like this, or this OH may come this side, the other side carbon may become carbocation. I hope we can understand that this is a 3-degree carbocation, this is a 1-degree carbocation. So always favor will be there for this one, not for the other one. Now I am adding the water, right now. So if ordinary water is added, anyhow this side one, that side one, OH comes. But instead of water, if 18, that is what? Labeled water I said. That is oxygen instead of the 16 oxygen. If 18 is there, it's an isotopic oxygen. Just like hydrogens you can take deuterated, but here oxygen I am interested. The old oxygen was 16-1 goes to the terminal, and a new oxygen that is O18 comes in the center. That to opposite configuration, isn't it? So 118 comes this side, means again here rotation, stereochemistry there is no important, but ordinary OH goes that side. The newly entered O18 comes for the alkyl side. Okay, this is what happens in the acidic medium hydrolysis. The newly added oxygen goes to the tertiary carbon because owing to the stability of the tertiary carbocation, right? In the basic medium, so you are adding water in presence of the OH minus, or you can take OR minus and so on. Here again O18 I am taking. When water is taken O18, it is deemed to understand the other oxygens also 18 because they get exchanged. You cannot have one labeled one without. So all are O18 only. Now in this reaction there is no plus attacking. So directly the anion will come and open up. Okay. So where will means let us say this OH is coming and attacking. It can attack on this carbon or on this carbon. It is a nucleophile, right? So this carbon has two plus I groups and one minus I group. This is bond common. So here there is no plus I groups, but withdrawing group is there. So this carbon will have a more electron rich center. So therefore the OH comes here and leading to formation of OH this side. That side you will get a O minus. Later on it become into that proton from water is taken, that will become into the OH. But O18 comes into the center of the tertiary carbon. That is rich, you know. Rich means the O minus attacks here, not here, right? So therefore O18 goes to the terminal carbon. O18 goes to the terminal carbon, and this carbon will have a O minus. Later on that also will become into OH. This will become OH, and that side carbon also will become O18. A diol is formed, glycol formation, there is no problem. But the O18 goes to where means in the basic medium the newly added O18 goes to the terminal carbon, because here there is no tertiary carbocation involvement. In this case protonation, that is oxonium ion, opens into carbocation either 1 degree, 3 degree. 3 degree is more stable, therefore the newly added water comes into the center. Here on the 2 carbon, this carbon is more electron rich, therefore the nucleophile attacks on the terminal carbon, that means new water or O18 goes to the terminal carbon, and here making the center one as a normal OH. So if you find with reference to the labeled water, exactly reverse type of answers are there. O18 goes to center, O18 goes to the terminal. But the stereochemistry is not important in this case, right? So epoxidation followed by hydrolysis. In the acidic medium, basic medium, no difference in the stereochemistry. But the whole mechanism is a trans only. Okay, permanganate addition is a cis type. Epoxidation followed by hydrolysis is a trans type of the addition, that is fixed. In the oxidation, there is another type of oxidation, is permanganate with acid, that is called acidified sulfuric acid, acidified KMNO4, acidified permanganate. Acidified means not HCl specifically, not HNO3. These two should be avoided. Why should we avoid means when I add HCl to the permanganate, HCl undergoes oxidation and Cl2 gas is liberated. So permanganate is so oxidative reagent, that to acidic medium strong oxidizing agent, therefore it oxidizes the Cl minus into the Cl2 gas. That's why that is danger. Nitric acid itself is an oxidizing agent, so two will become complicated issues, therefore avoid this one. Then what is allowed means dilute sulfuric acid is allowed. Okay, so you take this dilute sulfuric acid and permanganate, mix it. That solution is called what? Acidified permanganate, which is a stronger oxidizing agent than the KMNO4, that is alkaline KMNO4. Now we have an example I will take like this. An alkene containing one side 2 alkyl, one side 1 alkyl. Just for the benefit of the discussion, I have taken one side 2 alkyl, one side 1 alkyl containing alkyl. When added this KMNO4 in presence of the acidic medium, though I write H plus, the meaning is dilute sulfuric acid. Acidified KMNO4 also will have the pink color, decolorization you can observe here. So first what happens, the sigma bond will cut and you will get 2 OHs, but that will not be the end. That is happens in the alkaline KMNO4 also. But now what happens, another OH also cuts, you will get one more OH. That means initially what you will get is the 2 pi bonds are sigma bond also open up, and you will get this type of answer perhaps. That side also you will get like this, 2 OHs are formed. Both undergoes breakage, just like sigma bond, pi bond converts, alkaline KMNO4 converts, pi bond into the 2 OHs. Like that, even sigma bond also converts into 2 OHs. Therefore, this answer will be formed as an intermediate, but because of the 2 OHs unstable, so water molecule is lost from the both the side. So you will get one side a ketone is formed, other side you will get aldehyde. This is aldehyde. Now the problem is aldehyde is unstable one. So ketone is okay, but aldehyde is unstable because permanganate oxidizing acidic medium, strong oxidizing agent. So nascent oxygen will be available, that will be oxidizing the aldehyde into the acid. So finally what happened is, one side the side from the 2 alkyls gave ketone, that remains as such. But from the side of the 1 hydrogen 1 alkyl becomes into aldehyde, further oxidizes into the acid. So no more aldehyde at all, only ketone and the acid will be there. Which side ketone? 2 alkyl side ketone, that means a ketone containing 2 are same like in the case. 1 R containing this carbon becomes into acid. So 1 R containing acid and 2 R containing ketone will be final answer. If all the sides 4 R's are there, 2 ketones will come. Each side 1 R, 2 acids will come. This is the example, I said suitable example. Ketones and acids will be the answers, but aldehydes will not be the answer. Okay, right. So this is called acidified KMnO4. Variety of examples you can take as a 1-butene, 2-butene, substituted alkenes and so on. Ketone formed means on the alkene carbon 2 alkyls are there. 1 hydrogen if it is there, it comes into the acid. This is the essence of this acidified KMnO4. Lastly, we have one more oxidation, that is reaction with ozone called ozonolysis. We will see that. Fourth type of oxidation is called ozonolysis. In the ozonolysis, a double bond containing, again let us take one side 2 R's and one side 1 R and 1 hydrogen. Okay, it is suitable to discuss the reaction. So we are adding a ozone, followed by hydrolysis we do. These are the 2 steps reaction. Then the compound becomes into 2 pieces. One side you will get the carbonyl compound, 2 alkyl side it is definite, but the 1 alkyl side what comes is a slightly debatable type of the question, what comes from the other side. So that depends on the hydrolysis type. Hydrolysis is 2 types now. A is adding water and zinc, this is A type. B is only water. If I add zinc and water, you get the, let us say in the hydrolysis I am using this one, not this one. Okay, then I get aldehyde and ketone. Okay, ketone and aldehyde. Whereas if I use only water, the aldehyde will become into acid. So other option is there is no aldehyde, but its acid will be there. In this case you will get acid. Ketone will be common in both the cases, but aldehyde or acid, it depends on what type of hydrolysis you are doing. Water and zinc, only water. Only water means acid will be there. Water and zinc, aldehyde will be there. What exactly the mechanism taking place means? Let us see the little illustrative type. Ozone means it has a number of resonance structures. One of the resonance structure you can go for like this, plus and minus. So the plus and minus as a just like electrophile and nucleophile, it adds on the alkene and you will get like this oxygen, 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 then connection like this. Okay, and the groups will be as it is. Whatever the alkyl groups are taken intact, they are not going to change. Now this is called one in an ozone added molecule. We have 2 problems here. This OO bond is called a peroxy bond. There is a problem, there is a problem, 2 problems. This is not a problem. OO bonds, peroxy bonds are the problem. That's why it immediately one of the peroxy bond opens and that splits in other way. So, that comes from the other side, it rotates and then 2 O's comes from the downside. This is called a rearrangement reaction because nothing is added, internally rearrangement. So, this oxygen makes a bond from the top like this. The 2 other oxygens comes from the down. Now, the sigma bond totally cuts. Groups will be again intact, 2 R's one side, 1 R and hydrogen will be there. This is called actually the name of the alkene, say, then say ozonoide. Then what is this one? This is also ozone added, isn't it? It is called a mol ozonoide. Mol means not true one, false ozonoide it is. Both are unstable, not a stable one, but relatively this has only one peroxy bond, therefore somewhat more stable than this one. This is highly unstable, immediately changes into that one without any our intervention, but this can be stored for some time, but still it has a peroxy bond, slightly explosive type of quality is there. So, it can be further now treated with the hydrolysis. As I said already, in the hydrolysis we have 2 methodologies. One is water and zinc. Okay, water and zinc I add, that is A condition if I apply. The zinc takes away this oxygen, the middle oxygen liberated one goes with the zinc. So, zinc will become into zinc oxide is formed, right. Then what about these 2 pieces? This oxygen will be restored by this side. So, one will become into ketone with 2 R's. Other one will be carbonyl group with the aldehyde. 1 hydrogen, 1 R is aldehyde. This is a ketone. So, 1 ketone, 1 aldehyde, 1 zinc oxide is formed. Okay. Zinc is the now having some role here. Zinc will absorb that middle oxygen, becomes into zinc oxide. Instead of zinc, it is studied that some nascent hydrogen containing reagent if I use, the nascent hydrogen will take away the O, becomes into H2O. There are some methods like dimethyl sulfur, 2 sides methyl containing sulfur if I take, this takes this our oxygen, becomes into dimethyl sulfoxide. Dimethyl sulfoxide, it is known as DMSO, dimethyl sulfoxide it is. So, like that there are other methods are there to grab away this oxygen. So, in the simple way is zinc. Zinc takes away oxygen, becomes zinc oxide. So, zinc is reducing. So, therefore, I call this type of hydrolysis as a reductive ozonolysis because zinc is reducing. So, zinc reductive ozonolysis gives a ketone and aldehyde. Otherwise, I said other option for the hydrolysis is only water. In the only water, definitely that oxygen will be coming and waiting for to oxidize some molecule. So, this side you will get ketone, no problem. The other side you will get a aldehyde, isn't it? That aldehydes are more reactive than the ketone, therefore, this nascent oxygen will be adding and it gives finally what happens, an acid is formed. So, OH and a double bond O means it is an acid. So, acid and ketone will come in this case and ketone and aldehyde is formed in the other case. So, therefore, there are 2 different slight variation at the second stage, that is hydrolysis stage, but adding ozone is common, getting ozonoide is also common. So, this is called oxidative ozonolysis, using zinc is called reductive ozonolysis, right.